So my name is Tom Wickham-Jones. I'm the Director of Kernel Technology at Wolfram Research. The talk that I'm about to give is called Sprechen Sie Wolfram. It's about the Wolfram language. It'll talk about starting at the beginning of Mathematica, how we added the language and it was a powerful feature, and some of the aspects of the language that made it particularly attractive. I'm going to cover developments, enhancements that we've made to the language and the programming environment over the years, and then how we're trying to rebrand the language, turn it into the Wolfram language, and then finally ending up looking at new features in the upcoming version. Good morning, and I'll carry on with the sort of talks and things for the conference. So this is a talk, we're going to talk about the Wolfram language. So I'm going to take a somewhat of a historical perspective, or, you know, John was talking about new features. I'm going to go back, you know, from infinity to beyond, but end up with new features that we have in the new version. Right. So 1988, Mathematica 1 was released, and I think pretty early on people realized that the language that it provided then was a really interesting feature and something that attracted, was a key building block that attracted people to it. And I'll just remind people, some of you here will be newer to the system, some of you will be there at the beginning. So I'll just remind you, these were a couple of things that I found were useful sort of resources. This is the version 1 book of Mathematica, which was quite an interesting book, and I actually, this shows how, you know, it's a while ago, I went to a bookstore and I bought the book and I read it. The first version was quite small, the last printed version was bigger, and it had a lot of interesting, you know, features talking about programming and how the Mathematica language compared with other languages that was kind of useful. And another programming primer. There's been lots of books about programming in Mathematica. This was a fairly early one written by Roman Mader that I found quite kind of useful, and I think, you know, other people probably did as well. Right, so let's just have a little think about the language, Mathematica language itself. Many of these interactive. It's a very literate program. So Mathematica programs, often the words and things describe what they do. It's functional. When Mathematica was produced, functional languages were more exotic. Now they're more mainstream. Has a nice pattern matcher. And a lot of the system is written in terms of itself. That means that at Wolfram Research, we build a lot of the features for Mathematica. We build in terms of the language. And another feature of the language, I think, is that often Mathematica programs don't really look like Mathematica programs. So I might write something like, you know, random, real, just create some sort of type of, you know, sort of set of data, and that. And another, just a quick primer way of making a function definition would be, in fact, we could do, so I'm going to make a new function. This isn't a tutorial on Mathematica, but I just thought, so here's a function definition. So this is something that creates a set of numbers, and then I've defined a function that I can call and invoke like that. So that's just some real starters with Mathematica programming. But I think the thing that's most interesting, or one of the things that's particularly interesting, is this thing that sometimes we call the fundamental theorem of Mathematica, and John mentioned this, and this is that we have this uniform expression structure. So there's only one type of thing in Mathematica, and the programming language, the programming features and techniques work over many sorts of things, and Mathematica programs often work by changing and modifying these programs. So here's another example. And so I've made a plot. And what I'm going to do is I can use Mathematica programming techniques. So I can bring out, so it's a plot, so it's got a line thing in it, so I can find that with the cases function, and I can write a little program to take all of the lines and then reverse the points in all the lines. And so what this means, I mean, maybe this particular thing's not super interesting, but what this is saying is we don't need to build a special graphics manipulation language. We have it. By using this common way of representing everything in Mathematica, Mathematica programs will automatically be able to work with it. And that's a big benefit, because once you've understood the sort of common principles of the system, then you can apply those in many places. And I think that's a feature of Mathematica programming in general, is it allows people who aren't necessarily experts to build things that would be hard in other dedicated systems. Right. So let's go on. So here's some sort of history of Mathematica programming. We added in version 2 Mathematica 91, I think that came out, a bytecode compiler. And this was a way of speeding up the language. It works for a subset of the language. One of the things that we wanted to add this for was a lot of the numerical computation functions to get significant speed and memory enhancements. Then over the years, we've added development of this, code generation, and creating and linking dynamic libraries and multi-core operation. I'll just give a quick demo. So here's a compiled function. We get one of these summary types of things that we see here. So it shows the compiled function. And we can use this just like any other function in Mathematica. So to give it an input, and it returns the argument. Now, it has an expression structure. So the expression structure itself is a bytecode. So you don't have to read this because it's kind of detailed. But since it's an expression, we can write Mathematica programs to do things to it. And so one of the features is we have a disassembler that shows a textual representation of what the compiled function is doing. And this is the basis of our code generation features. So for example, with a similar type of functionality, I can then turn this into a C program. So it's taking the Mathematica code and generating a C program. And we have other tools that actually do the code generation, call the C compiler, link it back in automatically, which is all quite powerful. So the benefits of the Mathematica compiler is its speed, particularly the multi-core operations, but you can use the code generation, you can make standalone applications. And here's some little idea of the speed acceleration. So this is the parallel code, and it's smaller, which is good because this is time. Right. Another, on the time, a new feature that we added along the way was this thing called packed arrays. So this was a way of optimizing representations of vectors, matrices, and numbers tied to the compiler. This was benefits of this was this allowed much faster operations, like, for example, matrix operations, and improved memory usage. Right. So another feature of the language in Mathematica is that we've tried to make it possible to work, or programming in Mathematica is we tried to add integration into other languages. So these are some of the nicely supported languages that we can integrate with. And again, some of the benefits of this is it makes the system a bit less closed. You can integrate with other things. In the modern world, it's very likely you'll have different tools or people working with different languages, and Mathematica can be an integration between all of these, and you can add libraries from other languages. Right. Need to keep moving slightly quickly. So let's talk about symbolic programming. So I talked about that with the graphics example. Here's another example of this, which is we have these higher level building blocks. So we have the symbolic C and symbolic XML. And here's an example of some C programs. So this is a function, a whole function of C that I might have, but it stays as this sort of symbolic representation, this sort of tree structure that I can manipulate until I convert it into a string with this other function that converts it into a string. And again, that's the basis of the code generation. And in general, when you're working in a domain, very often it's quite a useful thing to identify the symbolic representation of your domain to build models and things, and then work on those. And in software engineering, you know, that can make a sort of model controller view type of workage, and that's you know, a natural thing in Mathematica. Another thing we'll probably talk a little bit about, I think a nice feature of Mathematica programming is this sort of computable documents, and you know, the documents themselves, as far as programming, they can contain the programs and the description and the data, and that's a useful programming feature. And one of the things about having the computable documents are also examples of symbolic structure. So I'm going to show a little bit more. This is I'm not going to show all of this, but this is the underlying data structure, the Mathematica symbolic structure for my talk presentation. And since they're Mathematica programs, Mathematica expressions, we can manipulate them with tools. We do this for our documentation system, various other things, and we have this new report generation tools that we've added in the new version. Right, programming, we added a development environment. So Wolfram Workbench, we called this. It's based upon the Eclipse IDE, and this is useful for, it's very much a traditional IDE based on Eclipse. So it had all sorts of, you know, specialized editor and refactoring tools and debugging and profiling, such like. And the nice thing is it integrates with other types of development environment tools that you might be interested in. And one of the reasons we did this was to try to make Mathematica, which has all these nice programming features, we wanted to try and make it more useful also, not just for sort of mathematician scientists, but we wanted to promote the use of with traditional software engineering techniques. And Mathematica has a lot of really powerful ways of doing traditional software engineering. We wanted to make it seem attractive for building big systems. And there's actually a white paper in the documentation that has some description of ideas and workflow practices that we've built up of how to do software engineering with Mathematica. And here are some of the things that I think are quite interesting for software engineering type things with Mathematica. So the symbolic representation of things in Mathematica, in software engineering, you talk about that as being serialization. Everything has a full form. It's very easy to serialize data out, and this is a very useful way when you have some big program. You can save out various parts of your data into files and use those for test cases. If you're working in a traditional language, like sort of Java or C# or something, you'd have to write special code to do that, but in Mathematica, it's just immediately available. Also in Mathematica, it's very easy to access different points of the code, and that's also useful for writing test cases. Some of the visualization tools are pretty useful, and sometimes it's quite powerful to drive your code inside and manipulate, and that's a great way of finding edge cases and unusual types of problems that you can then go and fix. And also, for example, some of the random number generation can build up sort of random models that can also be useful as test cases. So we went along like this for a long time. We like our language, but just as Conrad was talking about earlier, we did think a lot of the way that we present the language and how people perceive it. And I think Stephen even wrote a blog about, Stephen wrote a blog about what should we call the language of Mathematica. So the key problem really is that Mathematica sounds like it's doing math. Now, if you are doing math, of course, that's great. But we felt that it was something of an inhibition, that people in other domains might want to use it, but they felt, oh, Mathematica, well, it just does math. And we wanted to reach a broader audience, and I think the name of things is important. So then we thought about this, and we've decided that the name to give to it is WL, the Wolfram language. And in conjunction with this, or part of this, we're starting a major push to promote the language. Now, some of the ways that we're doing this is with some of our new cloud offerings. There are some talks later about some of our cloud offerings. One of the features of the cloud offerings is that they have different ways of assembling them. So we have a thing called Mathematica Online, which is very much like the sort of Mathematica notebook experience, except it's in a web browser. But in terms of programming, we also have a thing called the programming cloud. And this is something that's very much focused upon programming, building cloud and web deployed functions and programs, and as a sort of programming lab, but delivered over the cloud. And that's one way that we're trying to sort of promote the language. Right, so now I'm going to talk a little bit about some new features that we have in the core engine. I'm not going to go into these in too much detail, but I'll talk about some things that I think are particularly attractive. So I think one thing that is maybe one of the most innovative features that we've added for, many years, 10, 20 years, is this thing that we call association. And this is a new type of expression, so it's expression with a full form and everything, but it has some interesting uses. So you can use it like a programming structure, like an object or a record or a struct, but it also has some useful things. It's also a data structure, and so it has interesting data handling properties. So here's just kind of some basics. So this was this thing with angle bracket, and basically it's an associative array. You can see the full form, so it has like regular full form, and you can pick out the parts. So I can come to ask for the B element, and it returns 6. And I can sort of update it and everything. Now this is like a hash table, so the keys, these things that appear on the left-hand side, A and B, of course, they have to be unique. Definition. So again, here's one key thing, is it works similarly to a list, but it has named parts. So this is like a list. So you say the first part is A, the second part is B, and in the association world, here's an association, except now we're going to say the G4 part is B. So that's pretty much how it works in the system. If you want to have questions about how that works with structural operations, that's the answer. Talk about one of the features of association is it's built to be very optimized. So another detail, so one of the features of Mathematica also is that the expressions in Mathematica are immutable. That's a useful feature for Mathematica programs. So here I've made an association with 1,000,000 elements, and I can look up, get the x20th element. And I've also made a copy of it here. Now what I'm going to do is I'm going to modify this x20 element. I'm going to modify it, and that happens nice and quick. So now when I look up in the first version, I get the new value, but the old one has not changed. And so this is using, so when I did the update, that made a copy of the data structure, but it did it particularly fast. And this has some sort of clever data structure techniques to allow to allow these updates to happen so that the thing itself stays immutable, but it's all very fast. So that's a powerful feature of it. I'm not going to go into two, but I will just show this example. This might be a use for association. So this is in programming. So here I've got a function. It's going to create, and it's going to return, this is the old way of doing it, is I would return a list of different things. And then if I wanted to consume that data, I would have to pick out, to know that the dates were going to be the first part, and the names were going to be the second part. So in the new world, with association, I return an association. And I can make my code more legible, because I can say give the different elements in the structure a name. So when I work with them, I say, give me the dates part of the data, and give me the names. So this is much more literate. An example of using associations like objects in an object-oriented sense, but maybe I won't go into that just now. Another nice programming thing we've added is this unit testing. So Workbench has a nice unit testing framework. It's the same underlying application, but we've added a way of embedding this into a notebook. So I can add some tests, and so I have a couple of tests that I embed in this testing notebook, and then when I run them, it runs and it says, oh yes, well, this one here succeeded and this one here failed. So that's a useful way of building up knowledge and tests and things. The last few minutes I have, which are not many minutes, I will just mention the cloud programming features that we're adding. So these work in the cloud, and they also provide a nice way to integrate from so I'm integrating my desktop Mathematica with the cloud, and I can store expressions and things, and I can, as John was showing, I can also store functions. So things like with an API function, I can store that on the web, I can call it from within Mathematica, I can also call it from other types of place. And so I've gone sort of deployed a function. And then we also have this way of, so here's embed code. I'm generating here just HTML but I can also generate all these other languages for embedding the function in these different places. So that's the end of my presentation. This is a review of programming in Mathematica and the Wolfram language, and just trying to show you some of the key features and advances that we've made over the years, how it's a viable system for large-scale software engineering, talked about our vision for rebranding the language, and then some of the new features that we're coming out in the upcoming version. So thank you very much. Thank you.